Today on the Vulcan Way is 1.8 inverse functions. Let's get started. Okay, a couple of things we need to know about inverses. First of all, if you can compose f and g and get x, and do the same thing, g f of x, and both times you get x, not the same thing, but get specifically x, then two functions are said to be inverses. The notation for an inverse is a -1 sign, which shouldn't be that much of a shocker to you, because if you think about something like this, x to -3, that's the inverse or the multiplicative inverse of 1 over x cubed. So being consistent there. So that is f inverse. This right here is saying the same thing as this did right here, that if they are truly inverses, if you take one function and compose it of its inverse function, then you'll get x and vice versa. This right here is called the inverse function test. I'm just going to call it the inverse test. And when you do this, this is how you algebraically show that two functions are inverses of each other. Okay, moving on. The domain of f is equal to the range of its inverse and vice versa. Oh, that's just so awesome right there. And you'll see as we progress through logarithms and all kinds of other graphs that the fact that inverses, you just switch domain and range, which means you just switch x and y, is such a cool thing. And then also, another cool thing is that inverses are symmetric about this diagonal line with a slope of 1, y equals x. So its y-intercept is 0 and it has a slope of 1. So if you were asked to show that each function is the inverse of each other, and it shows part A is algebraically and part B is graphically, what you would do for the algebraically part is I like to set myself up. So I want to find out what f of g of x is, and I want to find out what g of f of x is. And if they both equal x, then they are inverses of each other. So let's take a look. F of g of x would be equal to 3. Take the g function and plug it in. That's the new input for f, and then subtract 1 and do your math. 3 times 1/3 is just 1, so you have 1x. And then same thing right here, you're just going to get 1, and then you combine like terms and we get x, which is what we were hoping to get, so that's awesome. Now let's go over here and make sure we get the same thing on this side. So we're starting with the g function, and its input is x, but now we're asked to put in f of x, so everywhere there's an x, we're putting in a 3x minus 1, and then to finish out the g function we have to add 1/3. Multiply, we get x minus 1/3 plus 1/3. Those two cancel each other out, and then we get x. So, show that each function is the inverse of each other. We would simply write a concluding statement here, because f of g of x and, that's important, g of f of x both equal x, they are inverses. Okay, so now we're going to move on to the graphically part. So how would we do this graphically? Basically, we need to graph each function and verify, using this bullet point up here, that they are symmetric with respect to the line y equals x. So let's graph some lines. So this first one right here is f of x, and it's 3x minus 1, so it has a y-intercept of -1, and then you go up 1, 2, 3 over 1. And then you are going to draw the line. I'm going to use a ruler because I'm cool like that. I prefer rulers, but I like my lines straight. But you could also just keep going like up 3 over 1. We're trying to prove a point here, so just that symmetry about the line y equals x. So that's why I'm going to do that. Whenever you have two graphs on the same coordinate plane, you want to make sure to label those. It's a good thing to be able to do. And then this other one is 1/3 x plus 1/3. I know there's a fractional y-intercept, but we can handle it. So 1/3 would be about right here. And then we're going to go up 1, so it would be up to 1 and 1/3 and over 3. So up 1 to 2 and 1/3 and then over 3. And then that will be our g function. So again, we're just kind of connecting these bullet points to these problems right here. And you're looking at this going, oh, okay, great, those are the graphs. How do I know that they're inverses? Well, the last bullet point says that they're symmetric with respect to the line y equals x. So here is the line y equals x. So we have a lot of different symmetries in math. We have our y-axis symmetry, our x-axis symmetry. We have a whole bunch of them. So this one right here is the line y equals x. And because you switch x and y, that should make sense, because if you switch x and y in this equation, you get the opposite. So we would get the inverses of each other right there. So that looks like that. So you can see this point, if I were to reflect it, would reflect over to that point, and so on and so forth. Okay? So I usually don't ask you to do something like that. I usually ask you to do something more like this right here. And it says, use the graph of f to draw the graph of its inverse function. So first of all, what I like to do with these ones is I have f. This one's going to be f of x, and then this table is going to be for the inverse of x. And then what I'm going to do to be able to graph its inverse, some people are like, well, Wolfgang, can't we just look at the line y equals x, which would be like right, you know, here-ish, and try and reflect. That's a really hard line for me to visually reflect upon, so I don't rely on my own vision. What I'm going to do is actually use another one of the bullet points from up above. I'm just going to pick like two or maybe like 3 or 4 key points. So I'm going to pick those 3, and I have this first point is -3, -2. And then my next point would be -1, 0. And then that point right there is 4, 2. And then what we're going to be using for this right here is this. The domain of f is equal to the range of the inverse and vice versa. So what that means for us here, x's are our domains, y's are our range. So I am literally just going to switch an x and y, because that's what it says, that they will be inverses of each other. So I have switched x and y. And then I'm going to draw those points on there. So -2, -3 here. That's that point reflected down there. 0, -1 would be right here. And then 2, 4 is right here. And you can see that we have now a beautiful reflected, nicely reflected, not eyeball reflected, very detailed graph of the inverse of the f function. Okay, so we've learned how to do that from a graph. Let's go ahead and learn how to find the inverse from an equation. So it's very similar, but there's a little couple tricks here and there. So first thing, to find the inverse, give it a try. Switch the x and the y. Now solve for y. You're almost done. Don't forget the -1. So there was a little kind of like song for you there. I'm going to put memorize on this, but I think if you know enough about inverses that you should be able to do this. So again, step 1, it's really like step 0, is to just change this f of x to a y just to help us out. And then you switch x and y. So again, because we get to switch their domain and range, we're switching x and y. Now solve for y. So I need to solve for that. So, and in this case, you can divide everything by 2, but I'm trying to get you guys in the habit of also seeing division by 2 as the same thing as multiplying by 1/2. So I'm leaving it like that for now. And so Solve for y. Now I'm solved for y. You're almost done. Don't forget the -1. So that's just to remind you that proper notation for inverse is that symbol, that -1. So if you have a G inverse, then of course that would be G inverse, and so on and so forth. So there we go there. Sweet. Okay, let's try the next one. So this one we might have to work around that other problem right there, but we'll be good. So for this one, for part B, first write it like this with the y instead of the f of x. To find the inverse, give it a try, switch the x and the y. So notice I'm just literally changing the x and the y. This x had a cubed. I didn't bring it over to the other side. The y gets the cubed because I'm only switching x and y. Now solve for y. Okay, so 4y cubed equals -x. Let's do it like this. Let's do x plus 1. And then divide by 4 or multiply by 1/4. It's up to you which one you want to do. So I am going to multiply by 1/4. And then the y has a cube on it, so we need to cube root. So cube roots are not like square roots. It's not plus and minus, so be aware of that. And this would be the cube root of 1/4 x plus 1/4. I just noticed that I did a kind of a inappropriate math thing right here. I shouldn't have taken the cube root like that. I definitely should have done 2 cube roots. So fix that up on your paper because you don't want to be caught doing something like that. So this is what our equation looks like, and then we'll just change it to the inverse form. And there we go. There it is. Okay, now C is my tricky, but we know with our trickies, these are really good thinking / test problems. So let's take a look at this one. You're like, I got this. I see what you're doing, and I can do this. Let's see. So first, we get to the first part, which is to switch, or just to switch the f of x to a y. To find the inverse, give it a try. Switch the x and the y. Here's the step where students tend to get confused or get lost. They're like, what do you want me to do next? And of course I want you to problem solve and think, what have I done whenever there's been a rational number before? So what we did then was we multiplied both sides by the denominator. So this isn't anything new. This side, the denominators will cancel out, and on this side I will get yx minus 3x equals 5y plus 2. And then from there, what I'm going to do is get my y's on one side because I'm trying to solve for y and I have 2 y's. The only way we're going to condense that to a single y is if we factor. So to factor it, I need the y's on one side and everything else on the other side. And then I can factor this out like that. That's pretty tricky, but also not so bad, just something that we might need to revisit over and over again before we take the test. So that's why we put things on our flashcards or on our cover-up list, so we make sure we do it. And then I'm just changing this to inverse notation. So to find the inverse, give it a try, switch the x and the y. Now solve for y, you're almost done. Don't forget the -1. Okay, moving on, horizontal line test. Now I know in Algebra 1 and in Algebra 2, you guys learned something called the vertical line test. And what the vertical line test does is it tells us whether or not the picture we're looking at is a function. So the vertical line test, just to recall, it's going to tell us whether or not the graph is a function. So I'll take you through that on these graphs here. So I'm not going to write anything down because it's asking us a different question, but here's what it is. If your graph can go through without touching, go through, a vertical line can pass through your graph without touching the vertical line twice, then it's at the same time, then it's a function. So something that wouldn't be a function, this would not pass the vertical line test right here, because all along this circle, there's one x value, say -1, corresponding to two different y values, so that doesn't work. That's like the boy asking two different girls to the prom, no players, that kind of situation. So if you notice on these, all of these graphs that we have here actually pass the vertical line test. That's because they're all functions. What we're learning about is something called the horizontal line test, and the horizontal line test says that a function will have an inverse that is also a function if there is no horizontal line that intersects the graph of the function at more than one point. So what I want you to know is that this is a picture of f. What we are testing for with the horizontal line test is to see if its inverse is also a function. So if we took the time to find some points on here, switch x and y, and do a vertical line test on it, we would know whether or not it was a function. But mathematicians were like, hey, we don't need to do all that work to see if its inverse will be a function. We can just switch x and y. So we did a vertical line test, but if we're talking about the inverse, then we can just switch it and do a horizontal line test. So as I scan this, will the inverse of this particular graph be a function? Yes. So I'm not even looking at the inverse graph, right? I'm not plotting points. I'm not doing anything like that. I am looking at a function, and I can tell right away if its inverse will be a function or not. I'm going to go to this parabola right here, and I'm going to take a look at it. And this parabola right here, look at that. There's 2 points throughout this parabola that are touching the pen, the horizontal line at the same time. So this would not be a function. And if you want to see real quickly, this is the point 1, 2, 3, 4, 5, 0, 5. And then this is the point, what point is that? That's 3, 0, and -3, 0. So real quickly, you can see I'm sketching the inverse graph. So this graph in black is f of x, and this is f inverse of x. Does it pass the vertical line test? The inverse graph does not pass the vertical line test, but again, those mathematicians, being the smart, lazy guys that they are, were like, well, if we do the horizontal line test, we don't even need to draw this graph, and we can tell that it's an inverse, or it's not an inverse, it's function. Its inverse is not a function. Okay, so let's go to this one. This one's also going to be no. And then this one right here, this one is passing everywhere. You might think that right here it's not. You might think, but it kind of looks. But with these arrows, this graph is just showing it's increasing. So this might be just a tiny, tiny increase. It might not be as increasing as fast as it is over here, but this is also a function. Okay? Its inverse is also a function. So go ahead and flip it over, and let's take a look. These are a little bit shorter notes today. So this one right here says to draw a function f where f inverse a is a function and where it's not a function. So this is just more thinking, like how creative can you get? If I want it to be a function, f needs to pass the vertical line test and the horizontal line test. Okay? So it has to pass both. If I don't want the inverse to be a function, but look, it does say that the original function is a function, the original f, so it must pass the vertical, but not the horizontal line test. So you've seen all types of graphs in math that could help you do this. So for example, here is a line that passes the vertical line test and the horizontal line test. Also, how about this guy? This is the square root function, f of x. F of x equals the square root of x. If somebody on this one right here was thinking and they were like, oh, I know one that doesn't pass, or I'm sorry, for part B, I know one that doesn't pass, and they drew me a circle, this would actually be marked wrong because the conditions say that you have to draw a function. So does this pass the vertical line test? No, so you didn't meet both conditions. So the first condition was to draw a function, and then the second condition is to have its inverse also be a function. and then in this one, not a function. So I'm going to be a little fancy. I don't know if you thought about this, but a square root graph does pass the horizontal line test, sorry, the vertical line test, but not the horizontal line test. So you could draw some other things on there as well, parabolas, that kind of thing. So one thing that we want to talk about with these is if something passes the vertical line test and the horizontal line test, then the function is said to be one-to-one. So if you look at this, it says the function is one-to-one in which no two different ordered pairs have the same y coordinate. Only one-to-one functions have inverses. So that's exactly what we're saying all along. So let's take a look at this. This is kind of like a pre-AP problem that you should be able to kind of put 2 and 2 together from. But what you need to know about one-to-one functions, this summed up is that f is a function and f inverse is also a function. That means that f passed both the vertical and horizontal line test. Okay, example 6, last example. Given that f of x and g of x are two one-to-one functions. So what do we know? Bam, bam. And that f of 2 equals 3 and g of 3 equals 1. Are f and g inverses of each other or not, and explain why or why not. So they're just telling us that there's some function f and some function g that are inverses, that are one-to-one. Doesn't say that they're inverses. We're asked to figure out if they're inverses. So what we're going to do is some good old-fashioned break it down problem solving. So what do we know? That's always a good place to start. We know that f of 2 equals 3. And if we convert this to points, this means that would be the point 2, 3. Yes? Okay. What else do we know? We know that when you plug in g of 3, you get 1. So that means that when x is 3, y is 1. The question is asking us if they're inverses and to explain why or why not. So there's lots of different ways you can explain this, but I'm going to put this up here. If f and g are inverses, then the point 3, 2 should be on the graph of g, right? So if 2, 3, to find inverses, you switch x and y, so the point 3, 2 should be on the graph of g. The point 3, 2 can't be on the graph of g because the point 3, 1 is already on the graph of g, little dot, dot, dot. If both points are on g, g wouldn't be a function, and thus wouldn't be one-to-one. Therefore, f and g are not inverses. So you might think, wow, we had to write a lot on that problem. Yeah, sometimes we have to really be thorough in our explanations. There's like a step-by-step process we need to meet or show that why we are not meeting that condition of inverses of each other. And we're using our one-to-one definition that we just learned as well. Alrighty, that's all we have for today. Until next time.